Jain student, my name is Pardeep and I am working as an assistant professor in IT department at Akgec Engineering College, Kajibad. So today we will discuss the very important topic of theory of automata and formal languages. Subject is pumping lemma for regular languages and context free languages. Pumping lemma for regular language and context free language. Okay, so before going into the depth of pumping lemma, so let's see some basic of language, that why we use pumping lemma, why it is required. So let's see, we know that suppose there is language, okay, and language can be finite and infinite. Okay, language can be finite and infinite. Okay, so if a language is finite, then it must be regular, then there is no issue. If a language is finite, then language is regular language. The problem is arise when language is infinite. Okay, so let's say if language is infinite, then there can be two conditions. If there is any pattern or loop, and there is one more situation in which there is no pattern. Language is infinite and there is no pattern. If there is no pattern, then definitely language must not be regular. Then language must not be regular. Then language must not be regular. But if there is some pattern and loop, okay, then we are going to use one method, that is pumping lemma test. Okay, we use the pumping lemma test. We are going to use the pumping lemma test. Basically, pumping lemma test is a negativity test. Means if the test pass, if pumping lemma test pass, then we can't say whether my language is regular or not. Okay, then language may or may not be regular. Then language may or may not be regular. We can't say. It is possible that it may be regular or it may not be regular. Regular, or you can say CFL. But if pumping lemma test fail, then definitely my language is not regular. My language is not regular. So let's see brief. So there is one language can be finite and infinite. If language is finite, then language is regular. If language is infinite, but there are two conditions. If there is no pattern, then definitely language must not be regular. But if there is some pattern or loop, then we go for pumping lemma test. Okay, but if pumping lemma test pass, then language may or may not be regular. If pumping lemma test fail, L is not regular. Okay, L is not regular. So it is a negativity test. It is a negativity test. It is a negativity test. Okay, means if it fail, then we can say language is not regular. So this is the basic of pumping lemma and about language. Now next move, let's see pumping lemma for regular language. Okay, so we have some infinite language, L, suppose infinite language L, and we apply the pumping lemma test on it. If pumping lemma test pass, then language may or may not be regular, and it is undecidable. Till now there is no algorithm by which we can identify that a particular language is regular or not. Okay, so if pumping lemma test pass, then language may or may not be regular. So to find out whether language is regular or not, it is undecidable, unsolvable, we can't solve. But if pumping lemma test fail, then language is not regular. We can decide that. If pumping lemma test fail, we can decide that language is not regular. Okay, so let's see the theorem of pumping lemma. So pumping lemma for regular language is used to prove that language are not regular. It is not used to identify whether a language is regular or not, but it is used to identify that my language is not regular. Okay, it is a negativity test. We cannot identify whether a language is regular. We identify whether a language is not regular, whether that language is not regular. That's why it is known as negativity test. We find the opposite of the regularity. So what theorem will say, if L is an infinite language, then there exists some positive integer p, okay, and p is also known as pumping length, such that any string w belongs to L stands for language, has length greater than or equal to p, that is length of string greater than or equal to p. Okay, means length of string, the string belongs to the language and length of string is greater than or equal to the pumping length. Then we divide this w into three parts, x, y, z, then it satisfies these three conditions. Okay, what it means? So there is language L. Okay, in this language there are various strings. So there is some string w. Okay, w belongs to language L. Okay, and there is some pumping length p. Okay, then mod of w, okay, is greater than or equal to p. Okay, and it must satisfy these three conditions. That means we divide w into three parts. Okay, there is string w, we divide w into three parts, x, y, z. Okay, and these three conditions must be satisfied. So mod of x, y, z is greater than or equal to p. This is the first condition, where p is the pumping length. Second is that length of y, means mod of y, is greater than or equal to 1, or in some books it is also written as mod of y is greater than 0. Both are same conditions. Okay, and the third condition is x mod of y belongs to L for all I greater than or equal to 0. So these three conditions must be satisfied. If any of these conditions fail, then we can definitely say that my language is not regular. Okay, so let's see one example for that. So prove that the language a raised to power n, b raised to power n, and n is greater than or equal to 1 is not a regular using pumping lemma. Okay, using pumping lemma. So let's solve it. So it must satisfy the three conditions. What are those three conditions? So let's write here these three conditions, that mod of x, y, z is greater than equal to p, where p is the pumping length. Second condition is mod of x, y is less than equal to p, and the third condition is mod of y is greater than 0. Okay, these are the three conditions. And fourth is x, y raised to power I z belongs to w for all I greater than equal to 0. These are the conditions. These conditions must be satisfied. So let's solve it. So suppose that my language is a raised to power n, b raised to power n. Okay, suppose that let L is regular. Okay, let L is regular. Okay, take any p value. Okay, suppose let p equal to 3. P is the pumping length. P is the pumping length. Okay, where P is the pumping length. P is the pumping length. Right? P is the pumping length. Now, suppose W equal to A raised to power P, B raised to power P. Now P is equal to 3. So A raised to power 3, B raised to power 3. Okay. So just open it. A, B, B and B. Now divide W into 3 parts, X, Y and Z. Divide W into 3 parts, X, Y and Z, such that this will satisfy these conditions. Okay. So let's divide these W into 3 parts. So suppose this part is X and A is Y and third part is Z. These are the 3 divisions I divide. Now check the condition one by one. Let's see the first condition. Now first condition is mod of x, y, z means mod of A, B, B, okay, equal to 6. This should be greater than equal to P. This 6 greater than equal, what is P? P is 3. So 6 is greater than 3. First condition is true. Okay. Now second condition, mod of x, y. What is x? X is A, and what is y? Y is A. Now length is 3. Now this 3 will be less than equal to P. This 3 will be less than equal to P. And what is P value? What is P value? P is 3. Now 3 is less than equal to 3. This condition is also true. Second condition is also true. Now let's see the third condition. Let's see the third condition. Now mod of y. What is y? Y is A. A means length is 2 and it is greater than 0. Third condition. Now 2 is greater than 0. this third condition is also true. Okay, these three condition is also true. Now let us see the fourth one. Okay, that x y I, this is x y I, z belongs to w for all I is greater than equal to 0. This must be satisfied. If any of the condition will fail, then we can say that condition is failed. Okay, now let us see the fourth condition, that x y raised to power I and z belongs to language L for all I greater than equal to 0. Okay, now w equal to a b b b. Okay, and we have divided this w, this x will be, a will be x, a will be y, and triple b is z. Okay, now put when I equal to 0, and just remember my language is a raised to power n, b raised to power n. This you must need to remember. Okay, when I equal to 0, then that x, what is x? A, what is y? A, and what is z? 3 times b. Okay, now put I equal to 0, put I equal to 0, so this will be equal to a raised to power 0 means epsilon. Okay, and 3 times b. A b b b. Okay, so this will be equal to a b raised to power 3. Is this string belongs to this language? Yes or no? No. This string belongs to this language, or yes or no? No. Okay, so this is, there is a contradiction, there is a contradiction. Okay, it says that for all I. Okay, if any one will not satisfied, then there is some contradiction. So a b power 3 does not belong to language L, so we can say that, so language L is not regular, language L is not regular. Okay, language L is not regular. Clear? Now see the next question. Next question, is prove that language L equal to a raised to power n square, where n is greater than equal to 0, is not regular using pumping lemma theorem. Okay, we apply the same procedure. Okay, so here let language L, which is equal to a raised to power n square, is regular. So let, okay, and here let w equal to a raised to power p square. Okay, a raised to power p square. Now we need to assume some p such that it will satisfy all the conditions. So suppose let p equal to 3. Okay, where p is the pumping length, where p is the pumping length, where p is the pumping length. Now w will become a raised to power 3 raised to power 2. which is equivalent to a raised to power 9 and which is equal to a 9 times a. Okay. Now let's suppose this a equal to x. We can divide any way. Okay, I am just dividing by one way. You can divide by any way such that all the condition will satisfy. Okay, a equal to y and 6 times a equal to z. Okay, now let's check the first condition. First condition is mod of x, y, z greater than equal to p. Okay. Now, what is x? X is a. What is y? Y is a. Y is a. And what is z? 6 times a. Okay, which is equivalent to 9. Length is 3, 3, 6 and 3, 9. Okay, 9 is greater than equal to p, and what is p? P is 3. So we can say that 9 is greater than 3. This condition is true. This condition is true. Okay. Now check for the second condition. Okay. Second condition, mod of x, y is less than equal to p. So see, what is x? X is a. What is y? Y is a. Okay. Now this must be less than equal to p. Now this length is 3 and what is p value? P value is 3. Now 3 is less than 3. This condition is also true. This condition is also true. Okay. Now see the third condition, that mod of y greater than 0, which is equivalent to, what is mod of y? Y is a greater than 0. We can say mod a length is 2. 2 is greater than 0. So this condition is also true. These three conditions are true. Now check for the fourth condition. Check for the fourth condition. So see the first condition, x, y, z greater than equal to p, x, y less than equal to p, and mod of y greater than 0. These three conditions are true. Now let's check the fourth condition. So the fourth condition is x, y raised to power I, z belongs to L for all I greater than equal to 0. Okay. And what is W? W is 9 times A. Okay. And we have already assumed, divided, that this A is x, this A is y, and this 6 times A is z. Okay. Now when I equal to 0, okay, when I equal to 0, then it W will be x means A, y means A, and z means 6 times A. Okay. I equal to 0 means A raised to power 0. So this will be A. Okay. Now anything power 0 in automata will be epsilon. So this is epsilon, okay, and this is 6 times a. So this will be a into epsilon is a, so this will be equivalent to 7 times a, and it is equal to a raised to power 7. Now our language L is a raised to power n square, okay, where n is some positive integer. Now it is not possible because 7 is not a square of any number, okay. So this a raised to power 7 does not belongs to language L. So there is contradiction. There is contradiction. There is some contradiction. So we can say that. So we can say that. So we can say that language is not regular. Why? Why not regular? Because here the test is failed. Here the test is failed. Pumping lemma test is failed here. Okay. So this is our initial condition, that if pumping lemma test fail, then language is not regular. If it will pass, language may or may not be regular. Language may or may not be regular. Okay. Fine. Now let's see one more example. Let's see one more example for pumping lemma that prove that a raised to power n, where n is a prime number, is not regular using the pumping lemma theorem. Using the pumping lemma theorem. So let's see. Let's see the solution of it. So let language L is equal to a raised to power n is regular. Let's suppose that language L is regular. Okay. Now let W equal to a raised to power p. We write the same. Okay, no difference. Fine. And where p is the pumping length, where p is the pumping length, where p is the pumping length. Okay. Let p equal to, you can assume any value, okay, 7. Okay, let p equal to 7. Right. Now W equal to a 7 times a. Now we divide this W into 3 parts. Okay, we divide W into 3 parts, x, y, z, such that it will satisfy the 3 conditions. What are those 3 conditions? The 3 conditions. Okay, first condition is mod of x, y, z less than, okay, sorry, greater than equal to p. Second condition is mod of x and y less than equal to p, and third condition is mod of y greater than 0. These 3 conditions, we need to divide W in such a way that these 3 conditions must be satisfied. Okay. So let's divide. Suppose a equivalent to x, a equivalent to y, and 3 times a equal to z. Okay. Now let's see these 3 conditions. Okay, mod of x, y, z means 7 times a less than equal, okay, greater than p, greater than equal to p. So length of 7 times a is 7. 7 is greater than equal to p. What is p? P is 7. So this condition is satisfied. Okay, this condition is satisfied. Okay, now see the second, that x, what is x? X is a, and what is y? A. Okay, is less than equal to p. Fine. The length of 4 times a is 4. 4 is less than equal to 7. This condition is also true. Okay, this condition is also true. This condition is also true. Let's see the third condition. Mod of y, what is y? A greater than 0. Okay. A length is 2. 2 is greater than 0. The third condition is also true. The third condition is also true. Okay, all these three conditions are true. Right. Now all these three conditions are true. Now let's see the fourth condition. Okay, fourth condition. Fourth condition will be x, y raised to power I and z belongs to language L for all I greater than equal to 0. Let's write correctly, greater than equal to 0. Okay, and here W is 7 times A. Okay, this is my W, and what is language? A raised to power n, and where n is a prime number, where n is a prime number. Okay, where n is a prime number, and we have divided this string, this AA into X, this AA into Y, and this 3 times A into Z. Okay, so let's check one by one. When I equal to 0, when I equal to 0, when I equal to 0, then W will be X. What is X here? A. What is Y? A, and what is Z? 3 times A. Okay, and Y raised to power I is 0, so I is 0. So value of this statement will be epsilon. Okay, epsilon means string of length 0. So it will be equivalent to A epsilon 3 times A. It will be A raised to power 5, and 5 is a prime number, so this A raised to power 5 belongs to language L. This will be satisfied. Now check for I equal to 1. When I equal to 1, so A X, Y A, and Z is 3 times A. I raised to power, I mean I equal to 1, so Y raised to power I, so this is equivalent to A raised to power 7. 7 is also a prime number, so this will also belongs to language L. Okay, if we find any one string, then there is some contradiction, and if we find some contradiction, then we can say that language is not regular. So let's see, when I equal to 2, so I equal to 2. Okay, 3 times A, this will be equivalent to this is a raised to power 2, this is a raised to power 2 into 4, and this is a raised to power 3, 3 4 7, so this is a raised to power 9. Okay, this is a raised to power 9. Whether this string belongs to language L, yes or no? Since 9 is not a prime number, 9 is not a prime number, so we can say that a raised to power 9 does not belong to language L. So a raised to power 9 does not belong to language L. So here is a contradiction. So here is a contradiction. So we can say that so language L is not regular. Why not regular? Because the pumping lemma test fails here. Okay, so this is about the pumping lemma for regular language. These are the most frequently asked question in various university examination, especially AKTU, and in various competitive exams. So this is for pumping lemma for regular language. By using these conditions, okay, we can identify that whether a language is regular or not. Regular is not regular. There is no such algorithm by which we can find out that language is regular. Let me write here. Okay, let me write here. Suppose there is language, okay, and whether the given language is regular or no regular, there is no direct algorithm. Okay, no algorithm exists. Okay, pumping lemma is a negativity test. It will tell that if it will fail, then language is not regular. It will not identify that language is regular. It will identify if pumping lemma test fail, then language is not regular. Okay, this is for pumping lemma for regular languages. Next, move on to the pumping lemma for the context free language. Okay, pumping lemma for the context free language. Pumping lemma for the context free languages. Pumping lemma for the context free languages. Okay, so suppose there is some language, there is some infinite language. Okay, if the language is suppose finite, suppose my language is finite, then it is always CFL, it is always CFL. Problem is arising when there is some infinite language. Problem arises with the infinite language. So there is some infinite language L, and we apply pumping lemma test on it. Okay, if pumping lemma test pass, we can't say whether language is regular or no, CFL or not. Okay, it may or may not be CFL. It is an undecidable problem. Okay, it is an undecidable problem. But if pumping lemma test fail, then we definitely can say that language is not CFL. We can definitely say that language is not CFL. And to identify that language is not CFL, it is a decidable problem, and to identify language is CFL, it is undecidable. Language is not CFL, it is decidable, and language is CFL, it is undecidable. There is no such algorithm to identify that language is CFL or no CFL. Okay, but language is not CFL, there is pumping lemma test. If it will fail, language is not CFL. So let's see. Pumping lemma for CFL is used to prove that certain languages are not context free. As I have told you that it is not for to identify that language is CFL. It is used to identify language is not CFL. Okay. So let's see the theorem. If L is an infinite language, then there exists some positive integer p. There exists some positive integer p, and p is the pumping length, such that any string w belongs to language L, okay, has length greater than and equal to p if w is divided into 5 parts, say x, y, u, v, w, x, y, then it must satisfy these conditions. Okay, that we need to divide w. So w belongs to language L, and we need to divide w into 5 parts, u, v, w, x, y, such that it must satisfy this condition. Okay, and if any of these condition will, if this condition at any instance, if this condition will fail, then we can say that pumping lemma test will fail. Okay, and we can say that language is not CFL. So let's see one example. So before okay, so let's see one example. Prove that language a raised to power n, where n is a prime number, is not a CFL context free language using pumping lemma theorem. Using pumping lemma theorem. So let's see. So let's see the solution. Okay, so let language L a raised to power n is a context free language. Is a context free language. Suppose it is a context free language. Okay, now w is equal to a raised to power p. Okay, these are the similar thing. Okay, and what is p here? P is the pumping length. P is the pumping length. P is the pumping length. Okay, so let's suppose let p equal to 6. P equal to 6. Let's suppose. Okay, NA. So now w equal to a A 6 times A, okay, 6 times A. Now we divide this W into 5 parts. What are those 5 parts? U, V, W, X and Y, okay. So let's divide these into 5 parts. Suppose this part is U, this part is V, this part is W, and suppose this part is X, and third part is remaining, okay, Y. So there is epsilon also, okay. Now this part is Y, okay. You can divide anyway, okay, you can divide anyway. And one more thing, it is not necessary that here I have written n is prime number, okay. There is no relation between pumping length and n, okay, there is no relation between pumping length and n, okay. I suppose n is string W and A raised to power P, okay, P is the pumping length, there is no relation between P and V. Note that P and N, there is no relation, okay, there is no relation between P and N, okay, between P and N there is no relation, okay. This is important. We need not to necessary to take P needs to be a prime number, okay. Now see the 3 conditions. So the first condition is let's see, let's write this condition here so that it will be easy, okay. Okay, first condition is VWX is less than equal to P. Second condition is V and X greater than equal to 1, okay. And third condition is third condition is, let me write here, U, V, W, X and Y, V raised to power I, X raised to power I belongs to L for all I greater than equal to 0. These are the 3 conditions, okay. So let's say one by one. Now first condition, VWX is less than equal to P. Now what is V here? V is A. What is X here? What is X here? What is W here? A. And what is X here? 3 times A, okay. This should be less than equal to P. So it is P less than, what is P? 6. So the first condition is true. First condition is true. Second is V and X greater than equal to 1, okay. What is V here? A. And what is X? 3 times A. Greater than equal to 1 means 4 is greater than equal to 1. This condition is also true. Let's see the third condition, that's the last condition, that U, V, I, W, X, I, Y belongs to language L for all I greater than equal to 0. okay, and A is W is 6 times A, where we have divided this A is U, this second is V, this third A is W, this third is W, this is X, and fourth one is Y. Okay, so let's see when I equal to 0, then W equal to A, now V is A and W is A, X 3 times A, and Y is epsilon. Now power is V raised to power 0 and X raised to power 0. Okay, so this is equivalent to, this will become epsilon, this also will become epsilon, so this is A square. This belongs to language L? Yes, this belongs to language L. Now put when I equal to 1, W equal to A epsilon. So this power is 1, it is also 1, so it will be A raised to power 6. This does not belongs to language L. So here is a contradiction, here is a contradiction. Okay, because why? So here pumping lemma test failed. So we can say that, so language L is not CFA, language L is not CFA. Okay, thank you.